Hi everyone, my name is Temur, and today I'll be presenting our work Performance Isolation for 5G RAN Slices across multiple interfering cells. This is work done in collaboration with my colleague Yongju, our collaborator Hetam, and my advisor Radhika. This work is motivated by how cellular networks are evolving. Operators aren't just running a single network, they're running multiple independent services on the same physical infrastructure. That's exactly what RAN slicing enables. So we'll start there. What RAN slicing basically means is that a single network operator, such as T-Mobile, can create logical partitions of its resources into multiple and allocate those resources to multiple independent slices. These slices can consist of application based slices such as resource allocation, isolated slices for robotics or drone control, or they can also represent MVNOs such as Mint Mobile or Google Fi. Each of these slices can have their own set of users, and each of these slices can also have their own set of unique objectives based on which they allocate resources to their users and schedule their users. Another interesting question to ponder over is that given the ubiquitous popularity of cellular networks, what happens when demand spikes and we need more capacity? So, in order to scale up the capacity of their deployments, what network operators usually do is that they augment the coverage of a macro cell, of a bigger cell, by deploying small cells within its own vicinity. And it is common practice for these small cells to operate on the same frequency as the macro cell to extract the maximum possible utility out of frequency spectrum, which is an extremely expensive and valuable resource. A consequence of this frequency reuse is that users who are in the overlapping regions between these cells tend to face interference and hence see deteriorated channel quality. In the past, people have looked at both of these problems in isolation. So we have looked at the people have looked at the problem of resource allocation for RAN slicing in single cell deployments, and people have also looked at the problem of multi-cell interference management without RAN slicing. The core thesis of our work is how is to be able to do both of these in conjunction. So essentially, how do we enable multi-objective RAN slicing? This is what our work Radio Ninja aims to do. Before diving into our work, let's start with some background. So in order to understand the challenge of our problems, let me tell you how each of these concepts are dealt with individually. First, we'll look at how resource allocation works in cellular networks and particularly in RAN slicing. So in cellular networks, how it works out is that you have a base station which covers a physical area. The resources that I'm talking about are arranged in this time frequency grid. Each of these boxes represents a resource block, um, which is the smallest unit of allocation which can be done to a user. The y-axis represents the frequency subchannel, and the x-axis represents the time slot for which it is allocated, called the transmission time interval. So in RAN slicing, how these resources are distributed is that based on some pre-agreed SLA, the network operator, T-Mobile, will allocate a partition of its resources to slice 1 and another partition of its resources to slice 2. And then each of these slices can have the illusion that they're operating on isolated physical infrastructure, and they can both schedule their users based on their own independent objectives, such as maximum throughput or proportional fairness, and they can schedule their users accordingly. So that was RAN slicing, resource allocation for RAN slicing. The other part is that I want to basically how do these passwords do interference management in the presence of multi-cell deployments? So how interference works out in multi-cell deployments is that we have a cell operating on a certain frequency. We augment its capacity by deploying a small cell nearby. We have a set of users, and all of these users are scheduled on the base stations that they're connected to. Now, given the fact that they are operating on the same frequency, a user which lies in the overlapping region between the two cells can face interference. So in this case, U1 is interference prone. A common which leads to a deteriorated channel quality for this user U1. A common strategy for mitigating the impact of this interference is to mute the interfering cell, in this case cell 1, on the frequency, the resource block that it is causing interference on. So in this case, cell 1 is muted on the first resource block, which leads to improved channel quality for U1 at cell 2. So given by taking this muting decision, we have a benefit, which is improved channel quality for U1, and we have a cost, which is that we have one less resource block at cell 1, and therefore user U2 does not get scheduled. So how do we reason about this muting decision? Essentially, we're benefiting one user and we're harming another user. So how do we compare this benefit versus cost across different users? And when is it acceptable to hinder one user to help out another? So in a non-slicing scenario where a single operator owns the entire infrastructure and all of its users belong to that same operator, an operator can have an objective such as maximizing throughput. So it can translate this lost resource block into some sort of throughput objective. For example, one less resource block means one less Mbps of throughput, and the improved channel quality means 4 Mbps gain in throughput. So as long as the benefit is greater than the cost, the operator decides to go ahead with the muting decision. But let's see how slicing complicates this. So instead of having a single slice with a single objective, now we have two independent slices, essentially two independent entities, each of them wanting performance isolation, and each of them working with a different objective. The problem is that different slices require performance isolation, but they're scheduled on the same resource block. If we go by the same technique that we used in the prior example where we only had a single objective, this is how the allocation would end up. We will improve the channel quality for U1 at the expense of not scheduling U2. But is that fair? Because essentially what we're doing is that we are improving the channel quality for U1, which belongs to the green slice, at the expense of U2, which belongs to the orange slice. So essentially, we're benefiting the green slice at the expense of the orange slice. And this violates the core promise of RAN slicing, which is to provide performance isolation. So how do we justify this choice? And moreover, even if we were to put performance isolation aside for a second, how do we even evaluate the utility of this decision across different metrics? So the orange slice thinks in terms of maximizing throughput, while for the green slice, the currency is proportional fairness, which is basically maximizing the sum of log of throughput. So these are two completely incomparable objectives. How do we even evaluate this decision across these different objectives? So, a simple naive solution which comes to mind is that the core problem is that we have a slice mismatch on the same frequency, which complicates things. How about we allocate the same resource block to the same slice across all the cells? So we update the allocation this way. So now we have the orange slice allocated on both the resource blocks, and we can simply take decisions maximizing the slice's objective while ensuring performance isolation. But there's a slight hiccup with that, which is related to the channel quality variation in wireless networks. So in wireless networks, different users, based on channel propagation characteristics, can have different utility associated with different resources. So I'll illustrate this through a quick example. So we can have a channel quality agnostic allocation where U3 and U1 are scheduled. U3 is scheduled on resource 1 and U1 is scheduled on resource 2. And this is the amount of data rate that they can achieve. And if we were to simply swap the allocations for the same users on those two frequencies, both of those users can do better. Everybody wins simply by being channel quality aware. Which channel is best for which user? Past work has shown that channel quality aware allocation can result in up to 72% higher throughput. So this means that this naive approach of just chaining the same frequency to the same slice across all the cells can lead to extreme underutilization of the frequency spectrum. So we cannot do this. This brings us back to our original problem, that how do we perform interference management while ensuring performance isolation between slices and enabling channel quality aware resource allocation. So in our work, we observe that the main idea the one key thing is that we should do fine-grained accountability of a muted resource. What we mean by that is that instead of thinking of a muted resource as a wasted resource, we count the muted resource as a resource consumed by the benefiting slice and deduct from its share at the muted cell. So in this case, cell the green slice benefits at cell 2. Its user U1 has improved channel quality. So slice 2's share at cell 1 is reduced. So essentially, U4 will not get scheduled and U2 still gets scheduled. So what's happening over here now is that the green slice makes a decision to improve the channel quality of one of its users on another base station while sacrificing one of its own other users. And this ensures that performance isolation is maintained. So it seems like we have boiled down the problem of muting to simply if the benefit of muting is greater than the cost of muting, we go ahead with the muting decision. But in our work, we learned that evaluating either side of this inequality comes up with its own share of challenges. How do we evaluate benefit and how do we evaluate cost? I'll briefly go through over the challenges that we face and we solve, and you can find the more details of it in the paper. So firstly, simply looking at improved channel quality as the benefit is wrong. Benefit is actually counterfactual. What I mean by that is that we need to know which users would have been scheduled without muting and which users would have been scheduled with muting in order to truly assess the delta created by muting. Secondly, true benefit in order to accurately so a muting decision creates a ripple effect across all of the future allocations. So in order to accurately assess the true benefit of muting, we need to constantly rerun the scheduler after every muting decision, which is prohibitively expensive given the sub-millisecond time bounds that we have. So in order to circumvent this, we come up with a fast heuristic to estimate the benefit from score deltas under the hypothesis of muting. As far as the challenges in calculating the cost are concerned, one thing that we do for fairness is that when multiple slices benefit from a single muting decision, the cost of muting is shared amongst all the benefiting slices. But this creates a chicken and egg cost attribution problem. Cost is split between the k benefiting slices, but after finding out the value of the cost, which was derived by 1 over k, one of the k slices might back out. Since this updates the fraction 1 over k, all of the k slices then reevaluate their cost benefit analysis again, and this cycle could go on. And lastly, this in order to accurately assess this cost as well, we once again have to rerun the scheduler, which is prohibitively expensive. And in order to circumvent that, we come up with this idea of a reference schedule where we run a schedule once. We estimate the utility per resource block for a given slice, and we use that to approximate decisions in our system. For evaluation, we do trace-driven evaluations using real-world cellular traces that we collect with up to 5 cells, 250 users, and 12 slices. Our baseline is Radio Saber, which is a channel quality aware scheduler without any interference management. We compare against two different schemes. One is single objective muting, which optimizes for one global metric across all slices, agnostic of the individual slice level objectives, and thus it violates slice level isolation and per slice objectives. And secondly, RSEP, which allocates the same set of frequency resources across all the cells without in order to similar to the naive solution that we discussed. So it loses out on the channel quality awareness aspect. The key result that we find is that Radio Ninja provides significant improvements while preserving slice level isolation and ensuring that no slice is worse off. So over here, we can see that with single objective muting, the throughput slice, the single objective muting with maximizing for throughput hurts the fairness slices. The one maximizing for proportional fairness hurts the throughput slices. Channel quality unaware allocation simply leads to an underutilized spectrum, while Radio Ninja consistently outperforms all of the other baselines, resulting in significant improvements for all the slices involved. So in conclusion, we identify a fundamental challenge in enabling future 5G deployments, which is how to enable multi-objective interference management for RAN slicing. We deal with two key challenges. First is ensuring performance isolation across slices, and secondly, reconciling slices with conflicting objectives. We do this by doing a per slice cost benefit trade-off without any aggregation across slices. The third challenge is to enable all of this in extremely tight sub-millisecond time bounds, and we utilize heuristics to approximate cost and benefit. And we observe that Radio Ninja provides 20 to 60% improvement in corresponding slice level objectives while ensuring performance isolation. Thank you.